In this video, let's talk about dynamic programming. Dynamic programming is solving the problem by figuring out the solution to the subproblems and then combining them to solve the original problem. It applies when the subproblems overlap with each other, because if we are able to store the intermediate results and use it later, we don't have to repeat ourselves when we combine the solutions. In the last video, we solved the coin change problem with the greedy algorithm, but had a problem where we cannot necessarily produce the optimum solution. And I also mentioned that we can use dynamic programming to solve the problem. So let's learn dynamic programming with the Fibonacci number problem first. This is called the Fibonacci sequence. Each number is decided by the sum of the two preceding numbers. It starts with 0 and 1. Then the next number is 0 plus 1, which is 1. And then the next should be 1 plus 1, which is 2. And then the next is 1 plus 2, which is 3, and so on. The problem is to figure out a way to return the nth number of the Fibonacci sequence. The first thing that comes to our mind is to use recursion. We can do that by returning the sum of fib of n-1 and fib of n-2. The first two numbers are given, which is 0 and 1, so we will add this if statement that can return 0 for fib 0 and 1 for fib 1, before the return, which will be our base case. And just to be clear, the Fibonacci sequence starts at the 0th index. Let's write out what's happening when we're calling fib. If you want to get the 6th number of the Fibonacci sequence, we will be returning the sum of fib 5 and fib 4. And to get fib 5, we need to call fib 4 and fib 3. And to get fib 4, we call fib 3 and fib 2. And this goes for every function call in this recursion process until we reach the base case. As you can see, if we want to calculate the 6th number, we need to go through this many calls. The time complexity of this approach will be roughly O of 2 to the n, because if we look at the tree shape, the time complexity will depend on how many calls this tree has. O of 2 to the n is pretty bad, so let's think about how we can make this process more efficient. The most frustrating part of this approach is that we are doing so much repetitive work. The first step of dynamic programming is to see what we're repeating and identify the subproblems. Look at fib 4. We are repeating fib 4 at these two places, resulting in a bunch of fib calls under each one. This is happening again for the other fib calls under fib 4. Can you see how each fib call is overlapping with the fib above it? Wouldn't it be very time-saving if we can store these intermediate results and use them instead of repeating the whole process in each function call? There is a word for this, and it's called memoization. It comes from memo. Let's use a map to store the intermediate results. The keys are the indices, and the values are the corresponding number in the Fibonacci sequence. We will initialize it with 0 and 1 for the first two numbers. Now, we need to store the Fibonacci numbers in this map. And to do that, we need to call each fib for all the n's. We will do that while following this path. Let's change our recursion fib function a little bit. We don't need to change the part where it returns the initial numbers 0 and 1, because we would still have to return 0 and 1 for the first two numbers, so we will leave that. Now, this is the plan. We are going to fill the memo map, and then we will return the one with the key n. That's our big plan to get the nth number of the Fibonacci sequence. For example, if we want to get fib 5, we can simply return memo at the index 5. But right now, memo 5 is empty. So if memo 5 is empty, we will assign it with this: fib of n-1 plus fib of n-2. So we assigned fib4 plus fib3 to memo5, and to do that, we need to call fib4. Memo4 is empty, so we assign fib3 plus fib2 to memo4. As we call fib3 for memo4, we assign fib2 plus fib1 to memo3 because memo3 is empty. As we call fib2, we put fib1 plus fib0 in memo2. Memo1 and memo0 are not empty this time because we filled up the initial values. Because of this if statement, fib1 will return 1 and fib0 will return 0. So 0 plus 1 is stored in memo2. When we already have a value for memo2, you can see how it just returns the Fibonacci value in memo2. This is why we're able to store memo3, memo4, and memo5 and eventually get the value of the fifth number. Once we pave our way through and fill up the memo map, can you notice how much repetition we avoided? If you see the number of calls in this approach, we are doing much less than before. This approach will result in roughly 2 times n steps. So the time complexity will be O of n instead of O of 2 to the n. But if you see how we get the stored values from the memo map, we are accessing the value sequentially. In other words, we first access from fib0, fib1, fib2, and so on. If we try to take advantage of that fact, we can come up with another approach that can save us some space. This is when the bottom-up approach comes in. What we did so far is the top-down approach because we are breaking down the problem from the top. Instead of starting out with trying to get fib5 with fib4 and fib3, we first calculate the second value with the 0th and the 1st, which we already know from the base cases. And with that, we calculate the 3rd, 4th, and 5th. So instead of using recursion, we can replace that with a for loop. With the top-down approach with memoization, we had to keep all the results in the map. But if we just use iterations to calculate the next number, we don't need a map. We just need these two variables that store the two previous values to compute the next number. This if statement stays the same because we need to deal with the fib0 and fib1 case. Then we'll say the previous value is p1 and assign 1, and the previous value as 0, which are the two initial values of the sequence. The for loop needs to say we'll iterate from 2 to n because the first loop will have to calculate the second value. Inside the for loop, we need to update p1 and p2. p1 should be the sum of p1 and p2, and p2 should become p1 minus p2. p2 should be the original value of p1 before the update, but we already added p2 to p1, so that's why we need to subtract p2. If this confuses you, just think that we are assigning the middle number of the updated p1 and p2 to p2, which is p1 minus p2. After looping until n, we will return p1. So that was dynamic programming. We will now see how we can solve the coin change problem correctly, but I'll do that in the next video.